Everybody, pretty much everybody in this session, I think, knows uh, quite a bit about pile driving. Here in Utah, we use H piles, and we also use pipe piles. Those are the two that we use. I don't think we've ever used pre-stressed concrete piles ever, other than in a research project that I know of. So the equipment that's used in pile driving includes a large equipment. It requires a crane that can hold the leads, and within the leads you put the pile, and then you have the hammer that is also being held up by the crane, and then it's the hammer that drives the pile into the ground. And then you've got a crane operator and a pile buck. He's the one in the very bottom of the picture. You see he's got a rope that controls, basically turns the hammer off once they get to the elevation that once they've met the driving criteria. So the UDOT pile driving specification, I'll be going over pretty much the entire specification but really just focusing on a few highlights of it. So the first thing is in the submittals, before a crane and hammer, actually before the hammer is brought to the site, there's a submittal that's required from the contractor that includes all of the hammer information. And that form, here's an example of that form filled out. And so that form needs to have all of the information that you see here, things like the ram weight, the rated energy of the hammer, the cushion information, and also the pile information that will be used. All of this information is needed by the designer to run a WEEP analysis. And with the WEEP analysis, then the designer determines whether or not the pile can be driven with that hammer. And so this submittal needs to be done before the hammer's brought to the site, because if the WEEP analysis shows that it cannot drive the hammer, cannot drive the pile, then we don't want the hammer to already have been mobilized and on site. So. So this just lists some of the, I can't quite see it, sorry. This is a neat microphone though, I can pull it off. Okay, so like I said, in Utah, we always do either pipe piles or H piles. And so the things that need to be included, this is really more for inspectors than it is for designers. So inspectors need to look on the plans to see what the pipe piles are, and then make sure that those piles are the ones that have been delivered to the site. For example, they need to meet the requirements of ASTM A252 steel for either grade 2 normal strength or grade 3 high strength steel. That's information that can be found on the plans. And the HP piles, similar type of thing. They either need to be a grade 36 or a grade 50 steel, again, according to the plans. And then the concrete. So for the pile driver, provide accurate test information regarding the yield stress values, or they're all otherwise known as the heat values, for each batch of piles to be used on the project. Of course, probably everybody here knows that that's an integral part of the design when a pile has to meet a certain strength. And so it's up to the contractor has to submit that information to the inspector, and the inspector needs to verify that indeed the required yield stress has been submitted to the project. So this just shows a typical pipe pile used on many Utah projects. And then this shows HP piles. So here's a typical plan sheet that shows the pile information, and there's important information on this that needs to be provided by the designer. And then once we're in construction, then the inspector, it's critical for the inspector to verify that all of the information that's on the sheet is being delivered. So we zoom in on some of the information that needs to be provided by the designer and verified by the inspector. This just shows the size of the pile, the diameter of the pile, and the thickness, the wall thickness of the pile needs to be shown on the plans. This one has, I've zoomed in on the notes a little bit, but it's probably still not enough for those on the back row, so I'll read through these. Note number 1, fill pile shells with Class A AE concrete with a strength of 3,000 PSI. Information that the designer has to provide. Number 2 is hold reinforced steel adequately in final position during placement of concrete around bars. So that's something that is included in the spec, but only for larger diameter piles. So, but I actually think that should be a requirement on every pipe pile. And so as a designer, you might consider adding that note to your plans. It just helps to make a better product in the end if you require that the steel is held in place until the concrete is placed around it. That's the reinforcement still in the pipe pile. Number 3 is use full welded drill mechanic. Let's see. I can't even read it, and I'm up this close. Use full welded or full mechanical connection splices as needed. Alternating bars allow 2-foot minimum between splices of adjacent bars. Number 4 is provide pipe material conforming to ASTM A252 grade 3 with a yield strength of 45 KSI. So this is where the designer has to provide that information, and then the inspector verifies in the field that the contractor brings that particular. In the spec it says use one or the other, but then it says according to the plans. So the designer has to put that information on the plans. Number 5, provide uncoated reinforcement for placement into piles. So it doesn't have to be coated reinforcement. It's very well protected by both the pipe and then the pile cap. With all of that protection, it's extremely unlikely that any moisture or any salts or anything are going to get to those reinforcements. So it does not need to be coated. Number 6, perform 1 PDA test at each quadrant of the bridge widening. So that is required in the specification. In this particular project, that I've used here for this example, the bridge, it was only one bridge, but it was rather wide. So the designer felt like it would be a really good idea to have a PDA test done at each corner of that bridge. And so they spelled it right out here on the plans. Of course, the plans take precedence over the specs. So if there's something like that that you feel needs to be on there, then the plans are the appropriate place to put it. Number 7, pile tip elevations are approximate. And the pile tip elevations are shown in this table, and I'll zoom in on it on another slide. So the pile elevations that are shown in this table are approximate. Verify at time of construction in accordance with the specifications. So what that's referring to is the PDA testing that we do. So the designer comes in and comes up with what is to be an estimated elevation that the piles will be driven to, but it's just an estimation. And so we have to make sure that the capacity that we need for that structure is there, and the way that we do that is we do pile PDA testing. Number 8 is pile hammer requires a minimum rated energy of 60 kip feet. So with that pile data sheet that was submitted, the designer runs a WEEP analysis, and they determine, actually even before that, during the design, the designer will determine whether or not a hammer can actually drive the pile. There's a few things that go into a WEEP analysis, and one of them is the size of the hammer, another one is the pile, and then the other thing is the soil profile. And so you have to have all three of those things to run a WEEP analysis. And so during the design, you may not know what the hammer is, and so you have to kind of make some assumptions. And with that, you run this WEEP analysis and you determine, okay, in order to get that pile into the ground without damaging the pile, you actually need a hammer of a certain amount of energy, which is in this case, 60 kip feet. And then they submit the pile driving submittal, the hammer submittal information, and then the designer runs a WEEP analysis again and to determine whether or not that particular hammer will indeed be able to drive the pile into the ground to the depth without damaging the pile, and to be able to verify the capacity of the pile. Number 9, see foundation plan sheet for additional pile data, including the pile numbers and locations. The hammer, the rated energy greater than or equal to the value indicated on the foundation plans. So I already showed you on the plans what that is. And again, that's something that has to be provided by the designer. Okay, does anybody know what this is? No, it's a pile driver. No, that's right, it's a fence post driver, right, hammer. But that's really what a fence post hammer is. It's a pile driver. It's a similar idea where you have a mass that's dropped on the object that you're trying to drive into the ground, and it imparts the energy to that object, and then the object goes into the ground. So here's a diesel hammer. Quickly, there's the piston, or in other words, the ram, and it has a certain mass. Some of the hammers in our state that are used quite often have about 6,600 pound is what they weigh. That's probably the most commonly used hammer. And then the way it works is initially the ram is actually picked up by the crane, and then it gets to a certain point and the ram is released, the piston is released, and then it falls a certain distance, and then it gets down to this pump actuator, which is a trigger. It triggers it triggers the diesel pump, and then the diesel pump shoots a jet of diesel fuel into the chamber, and then when the ram hits the bottom, the fuel is injected and there's an explosion, and it causes the piston to rise again. And so if when the ram hits the bottom and the pile moves significantly, then the ram, every force has an equal and opposite reaction. And so if that pile moves significantly, then the ram will not rebound as high as it would if the pile doesn't move very much. If that makes sense. If the pile doesn't move very much, then once the ram hits the bottom and that explosion occurs, then the piston, the ram, has every opportunity to rise up as high as it can. And those are critical things, because when we get to the point of accepting a pile, the things that are critical in that are how high that ram rises or falls, same thing, and how many blows are in 1 foot. And I'll show that a little bit more. In fact, I'll talk about it right here. So this is the dynamic formula in principle, and this is overly simplified, but it's perfect to demonstrate the importance of the stroke height, the height of the hammer H, and its importance in all of this, and also the weight of the hammer. So what it's saying is you impart energy using the hammer, and that energy will be equal to the work that is done on the pile. So the energy is just the weight of the hammer multiplied by the height of the fall of the hammer. So a force times a distance is the energy. And so that's the amount of energy that's imparted into the pile. So, and that's going to equal to the resistance that the soil is providing, multiplied by the displacement that the pile moves. Again, it's overly simplified from what really happens, because in the real life there's quite a bit of energy loss that occurs from several different things, but just for the purposes, really for pile acceptance during pile driving, this is a really good way to look at it. Okay, so here's the less simplified way to look at it, and I just show it to show that there's a lot more to it than what I just said. In reality, what happens is the soil profile is split up into increments, and each increment there is a spring and a dash pot, and when you do a pile driving analysis, you do a CAPWAP analysis, and with that, what happens is a wave, when the hammer hits the top of the pile, a wave is sent through the pile, and then waves are also reflected. And with that information, you can determine exactly where the resistance is occurring at each segment, and also at the toe of the pile. And with that, it's again, the only reason I show this is to show that it's not as simple as I showed in the last slide. So another reason we do pile driving analysis is to make sure that the piles don't get overstressed. And so that's what's happened here, that you can see that one pile is bent quite badly. And so the yield stress was exceeded in this case. So the pile was actually hitting that pile, the hammer was hitting the pile too hard for too long, and it started bending it. And so the PDA allows us to limit that. One thing that you need to remember also is that these piles have feelings. And I found that out on this project because when I took a picture from a different angle, you'll notice that the pile was reaching his hands out and letting me know that he didn't like what was going on. So here's the pile data, back to the pile data sheet. And the required minimum driving distance is determined by the designer. And so that's the value that we need to exceed when we do a PDA test on the first pile at each foundation. And then the other information that's critical is ultimate pile tip elevation. Or sorry, not ultimate, estimated. I explained that in that note that said that that's the estimated elevation, not the actual elevation. The estimated is what the designer estimates it's going to be, and then we do the PDA test to determine what it actually is, because with PDA testing, you figure out what the actual pile capacity is. And then the elevation of minimum acceptable pile penetration, and that's based off of, the designer also determines that based off what is needed for lateral resistance, settlement, I should have listed them. There's two more, I think. You guys can probably help me. Uplift, thank you. Uplift. And then there was one other one. Let's see, lateral, settlement, uplift. Down drag? I don't think it was down drag. Huh. All right, that's your assignment, is to think about what the fourth one could be. It seems like I think I had four things that needed to be determined. But anyway, based on those things, one of those will govern how deep the pile has to go as a minimum. And so when we do PDA testing, well, let me just point out that in this case, the difference between those two values is 20 feet. So what that means is you can, in this case, you can drive it, and if you meet resistance above an elevation of 4405, then it's not deep enough. And so in that case, what would need to happen is pre-drilling. We'd have to go in and pre-drill down to get through whatever layer's holding it up so that we can get to that depth. Scour, that's what it was. Yeah, scour. Good, thanks. You get an A. Yeah. And then the estimated pile tip elevation is what the designer thinks will actually happen when we're in the field, and what will actually give us the required capacity for that pile. And again, that's estimated. So once you get past the minimum, then we do the PDA testing to determine exactly what depth we need in order to get the capacity. I think we already covered that sheet there. So the okay, so this is getting into more of the details of the PDA testing. The department or a department authorized geotechnical firm conducts at least one high strain dynamic test according to ASTM D 4845 for each foundation, which means abutment, bent, or pier foundation. and that's a little more restrictive than what AASHTO may require. I think AASHTO LRFD requirements are closer to this now than what they used to be. In fact, they now might be identical to this, but I'm not sure. But just so you know, the department requires that it's done at each abutment, bent, or pier foundation. The department performs this test using pile driving analysis, PDA equipment, or driving the first pile at each abutment and bent pier foundation. The department evaluates the driving resistance and establishes driving criteria using a wave equation analysis program with signal matching. That's what the CAPWAP analysis is. So PDA is pile driving analysis, and then a CAPWAP is actually a wave equation analysis program. That's the signal matching part of it. Do not drive other piles in the foundation until the department gives notice that the test results indicate that sufficient capacity has been obtained and the driving criteria for the remainder of the piles in the foundation has been established. So at that point, the driving criteria consists of three things. The minimum depth, you now know what depth you need to get your capacity. And the other two things are the blow count, which is how many blows per foot, and the stroke height. And any one of those is not less important than any of the others. All three of those are critical, are very important to the pile driving criteria. So this is the instruments that we attach to the piles. The large one in the middle is a strain gauge. The one on the right is an accelerometer. This is an H pile, so those identical instruments are on the back or on the opposite side, directly across. Well, the strain gauges are back to back, and then there's an accelerometer here that you can see, and then there's another one on the reverse side there. And then we hook up those instruments to our computer and the PDA box and run the test. And if you've been around a few too many piles, you might start looking like that guy on the right. Maybe he got hit once with a pile with a hammer or something. I don't know. So here's an example of a pile driving record. There's actually two sheets to this example. The first one just lists the pile information up at the top. And then that middle stuff is actually filled in after the pile is completed. So if I can, I might come back to that. And then here's the actual pile information during the driving. So notice that there is, what are the three things that are required in a pile driving acceptance? Good. Okay, so the tip, there's the depth, and then the blow counts, the blows per foot, that's what's in this column here, and then the stroke, which is how far the hammer falls, and that's shown here. So that information, the best way to get that information is to use a saxometer. And when you take the average, even if you're doing it by hand, once you take the average over an entire foot, if you take 8 blows an entire foot, then that average value is actually very, very accurate from what we have found, easily within the nearest tenth of a foot. I would say if you've got 6 or more blows in a foot, then you can rely on that stroke value quite well. And we actually have the saxometer equation programmed in our HP 48G or GX calculators. So if you need that, we can just transfer it to you very easily. Another way to estimate the stroke is to find out how far, when the hammer comes up out of the top of the diesel hammer, when the ram comes up out of the top of the diesel hammer, you should know before the project starts, the hammer's laying on the ground when you first get there. Take advantage of that opportunity and measure how far from the top of the hammer to the top of the ram. So then when it's actually working in the field, when you see that ram come up out of the top of that, then you know what that stroke is. And in other words, if you've measured the top of the ram, the distance between the top of the ram and the top of the hammer, and I just did one the other day and it was 8 feet. So then during pile driving, as soon as you start seeing the ram come up out of the top of there, that's an 8-foot stroke. And if you, again, once you see 3 or 4 or 5, for sure, by the time you see 6 blows, if it's rising to the same point every time, then you've got a really good estimation of what that stroke is. And I think by eye you can probably estimate it. Well, you can easily estimate it to the nearest half a foot, and I think you could probably estimate it to the nearest quarter of a foot if you watch it for like I said, 5 or 6 blows. So that's the stroke. The blows, pretty straightforward. How many times the ram hits the pile in 1 foot increment. So let's say that we did the PDA test on this pile. What would the driving criteria end up being? Let me just say that we did a PDA test on this, and the capacity was measured to be, let's say the required capacity was 500 kips. And with the PDA and the CAPWAP analysis, we found out that the actual pile capacity was 510 kips. So given that information, what would be a good driving criteria be? I should also clarify and say that the PDA testing was done at that final elevation too. So with that information, I would say that the blow count criteria, because it only exceeded the required driving capacity by 10 kips, you needed 500 and you only got 510, so you barely got there, then I would say that that's your driving criteria. 20 blows per foot with a 9.1 foot stroke. So then the next pile that you drive, here's the information. So now, did this meet the driving criteria? If you can't see it, it's driven to 112 feet. The blow counts are 22 blows per foot, and the stroke is 8.9 feet. So there's your driving criteria. And there's I would say it didn't pass. It's very close. And the reason it didn't is, number one, this one's at 113 feet. The blow counts are 20. The blow counts for the other was 22, so the blow counts were higher. But notice the stroke here is 9.1 feet. In the other case, it was 8.9. So it was not imparting quite enough energy. And again, that seems like it's really close, but remember that the CAPWAP analysis got 510 kips, whereas the required was 500 kips. So it just barely passed. So that's, it's close, but it's not quite there. My guess is this, and the other thing is, it's 113 foot depth for the driving criteria, that the minimum depth, and this one only went to 112. So my guess is if they drive it that extra foot that they're required to do, they'd probably get it. They'd probably get that blow count and the stroke that they need. So just an example. And then back to this information. When it's all completed, you measure the plumbness and the pile location. There are penalties that apply if either of those values are too far out of requirements. They actually have, for the pile center, they can actually be up to 6 inches out without any penalty. And then the penalties start to kick in. And if they're a foot out, then not only do they not get paid for that pile, but it has to be analyzed to see if we need to drive another pile or what exactly needs to be done. And we show this example because this is showing that, okay, yes, it's 5 inches out in the north direction, 5 inches out in the west direction. 5 inches doesn't cause any penalties, but when you do Pythagorean's theorem, the 5 squared plus 5 squared equals, in this case, 7.07 squared. So now the 7 inches is out of, it is within, it's out of the tolerance zone, and so a penalty now does apply in this case. So the plumbness, it can be out as much as 2% before a penalty starts to kick in. So in this case, the plumbness would be fine, so there's no penalty applied. But the pile center is out, so a penalty does apply. Notify the engineer if any of the remaining piles in the foundation do not meet the established driving criteria before moving the hammer away from the abutment area or the bent area, or if driving conditions otherwise change. The department may require testing additional piles and reestablishing driving criteria for the remaining piles within the foundation. This is important. I've had a job where they actually moved the pile out, and as I looked at the driving of several of the piles, they did not meet the criteria, and so they actually had to remobilize the crane and the hammer and everything back to verify that the piles that didn't meet the driving criteria were okay. And you can imagine how unhappy that, or how happy that made them not. This sort of thing will happen occasionally where you establish driving criteria and then you continue on, an abutment's 100 feet wide sometimes, and you establish the criteria at one end, and they start driving, and pretty soon after about 5 or 6 piles, things change. That happens quite a bit. It's soil, it's going to happen. As soon as that starts to change, if it becomes drastic, then let's go out and test another one and establish new driving criteria for the remainder of the piles. So, another good thing to keep in mind on pile driving jobs. Perform a restrike PDA test on the pile after a sufficient time period, 24 hours or more after the initial driving of the pile. We've included this because sometimes you'll go out and you'll do a PDA test on an initial drive and you will not get capacity. In that instance, they have the option, if they want, to wait 24 hours and the pile can set up. The pore pressures will dissipate and you'll actually get an increase in pile capacity. But there's another reason why we included this in here. Any ideas what other reason we may want? Yes, dilatancy, thank you. Pile relaxation. So if during the design you ever have soils that might show any sort of tendency toward dilatancy or relaxation, what happens in that case is you drive the pile one day and then the next day there's actually less capacity on the pile. It's called relaxation. The soil relaxes and then the pile has less capacity. And usually in silty soils, so when you're in that, make sure you check for dilatancy and even require that the pile is retested, or you could require that, well, the interesting thing about pile driving is you want to do an initial drive so that you can make sure that the pile is not overstressed during driving. But there's also advantages to waiting for a restrike test for both pile relaxation or the opposite, where you can get additional capacity if the pile sets up. So that's something that the designer really has to kind of, you have to weigh all of those things. Pile relaxation is actually kind of a rare occurrence, but we have had it in Utah. And so it's always something to keep in the back of your mind when you're doing a design. And like I said, it's silty soils generally that will show the delatency. So if there's any doubt, I would say as a designer you should require, just put it right on the plans that a restrike test must be done. Butt weld the entire pile cross-section using full penetration welds according to AWS D11 for pipe piles and AASHTO AWS D1.5 for HP section piles. Information that can also be put on the plans if you feel as a designer that it ought to be more restrictive than that. Keep driven piles within 6 inches of the designated plan location and within 2% of vertical plumb throughout the total length of the pile, including bending. This is roughly equivalent to 1/4 inch in a foot or 0.6 inches in 30 inches. Receive approval from the engineer that these criteria have been met at the end of the pile driving before proceeding with backfilling or other associated foundation work. And why is that? It's because that's our opportunity to take care of something if there is an issue. Notify the department to determine the appropriate resolution if either requirement is not met. Contractor bears all costs for any measures required to resolve the nonconformance, including the price reduction factors shown in Table 1 in this section, Article 3.5, which we'll look at that in just a minute. So if the criteria have not been met, the engineer needs to know, the structural engineer will do an evaluation to see if it's detrimental to the structure. So it's critical that the structural engineer is informed. Drive additional piles as required to replace damaged piles and piles driven out of plumb or plan location at locations designated by the engineer. Again, if the structural engineer determines that a pile is out of tolerance and it's detrimental to the structure, then the structural engineer will also say, okay, we need another pile or some other solution. And if it's another pile, they'll actually specify the location of where that additional pile needs to be placed. Notify the Department of water collecting in open pipe piles. What does that mean if there's water starting to collect in a pipe pile? Yeah, it means that there's some sort of damage. It could be in a weld or during pile driving, there's some damage to that pile. So we need to know if there's water collecting inside that pipe, in that pile. Drive additional piles as described above and abandon damaged piles as directed by the department as necessary to resolve concerns with pile damage. Keep sides of piles at least 9 inches away from the nearest edge of pile cap. Receive approval from the engineer before concrete placement in pipe piles. Again, that's kind of a critical moment, because if once they place concrete in a pile, it's pretty difficult to fix a problem if there is a problem. So it's almost a checkpoint. I think it is a checkpoint actually, where before they place concrete in a pile, then the contractor should receive approval from the engineer. Place the rebar cage into the driven pile when the concrete reaches the planned bottom elevation of the rebar for piles larger than 18 inches in diameter, or 16. I think that's actually 16 inches. And I think that you can require that on a smaller diameter pile. I don't think there's anything wrong with requiring that on a smaller diameter pile. Support the rebar cage from the top so it remains within 2 inches of the required vertical location until the concrete reaches the top of the pile. Yeah, we don't want the cage sinking into the concrete. Secure rebar cage in position until concrete is set. Okay, now we're getting to the price adjustment, the penalties for piles that are out of alignment or out of location. So first of all, there's a reduction for deficient strength of concrete, and that's covered here and also in section 03055. And then a price adjustment for reduction out of tolerance piles, and those anytime there is any sort of price adjustment applied, then there has to be a demonstration of the technical adequacy of the piles driven out of plumb or plan location. And then these are the penalties. The department will accept piles according to this section. They'll reject any pile driven outside of the upper deviation limits, which in this case, before the penalties apply, they can be out of location 6 inches and then up to another 6 inches before the penalty is 0. The pay factor is 0, and the pile is also rejected at that point. And then the plumbness is a 5% at that point. So the department will apply pay factors to each pile individually based on the total measured pile length from the specified cutoff elevation, and apply only the criteria with the lowest pay factor for any one pile. So if one pile is 9 inches out and the plumb is 2.9%, then the 9 inches from out of location is what will govern, because it has the stronger penalty, and so that's the only one that is applied to that pile. I've just got a few pictures that show just some things to look for. In this case, that one pile is not straight at all. For inspectors, most of the contractors know that the most important part of driving a pile straight is the very, very first 10 feet or so. And the proper way to do it is to hit it a few times. Well, actually, level it up, make sure it's vertical, hit it a few times, stop, and do that again, and keep doing that for 10 feet. Because once you get it, if you can get it started straight, most of the time it'll go in straight, probably greater than 90% of the time. So it's that first 10 to 15 feet that's the critical to get it started correctly. This is more of a piece of art than it is engineering, I guess, but you can see that these got way out of plumb. I think, yeah. So these same piles, once they cut it off, they measured the locations, and actually, a lot of them were okay as far as the location penalty. You can see that one of them's obviously a reject, but most of the others are probably within that 6 inches. This one's close, borderline, but the plumbness on that previous picture was the thing that's going to govern in this instance. Can't remember why I put this one in here. Oh, this one, something to keep in mind. They drove these sheet piles. This is along the Jordan River, actually, and they drove the sheet piles to push the river over so that they could drive the piles. And then they removed the sheet piles. Well, how do you remove sheet piles? You apply an intense vibration to those sheet piles as you pull them up. Well, as soon as they did that, the existing bridge immediately just started sinking into the ground. Well, the soils in this case consist of loose sands, and the old bridge the piles only went into that sand. They didn't go any deeper. So those loose sands were actually liquefying, and the bridge started to sink into the ground. So it's something that nobody thought of. And so it's a good thing to keep in mind, I guess, when you're designing. I can't remember why I put that one in there, maybe just to show the marks on the piles when you're doing when the inspectors are doing the blow counts. Each one of those marks represents 1 foot, and so you count the blows per foot as they're driving. This picture's more for inspectors. When you're out there, you're going to get dirty. A diesel hammer is extremely dirty, messy, and once that black oil, I think that hammer's actually a red hammer, but you could never tell because it's completely covered in black oil. And once that oil gets on your clothes, they're done. You can't get that oil out of your clothes. So, and another thing is safety. These guys are the pile bucks, and they know what they're doing. If they ask you to get out of the way, get out of the way. Listen to them. Let them do their job. Keep your distance. Don't approach the pile. Don't approach the hammer until it's sitting down on the pile. Again, let them do their job and listen to them if they're telling you to get out of the way or whatever. I show this one because the pile, everybody's looking down at the pile, making sure that it's in the right location, and the designer designed it so that the pile, it's a widening, so the pile's going to be where it's going to be and everything. Well, one thing that you don't think of when you're a designer, at least I don't think I would think of it, is when you have an existing bridge there, you don't think about driving this new pile and the proximity to the existing bridge. And so then the hammer comes down and gets to that point. And I think this was John's job, and I think he said that it was fine as long as you take into account the resistance of the bridge when the hammer gets to that point, when the hammer starts hitting the bridge. So. Oh, okay. Darren's. Is Darren here? It was Darren's job. I think that's all I had for my presentation. But does anybody have any questions or comments?